Good afternoon, everyone. Within the next 15, maybe 15 minutes, we will talk about flow sensors as well. We talked about. And I will introduce to you a micromachine membrane-based thermoelectric flow sensor, which is the smallest version of the one we saw some minutes before. It's for two-dimensional measurement in this case, and it has a relatively high angular resolution. Two-dimensional measurements means in this case we measure the direction of the flow and the flow speed at the same time. So my lecture is structured as follows. I will start with a short motivation, and then I will show you the design of our new chip and some main steps of the fabrication process. Afterwards, there will be the results of the characterization, and at the end, there will be a short conclusion to summarize it. So let's jump in. At the beginning, there's a project, and the project is called COOL. It's a comprehensive project with 8 partners from different disciplines. And the aim of this project is the reduction of the power consumption of cold storage warehouses, especially for Apple storage warehouses. Apples are stored at around about 0 degrees, and they are very big fans, and those fans run the whole time, 7 days, 24 hours. And we try to reduce the power consumption for this fan and to reduce the fan speed. And for this case, we built an array of anemometers, of wireless anemometers. You can see here, the sides of the boxes, and to detect the flow and make a flow map of the whole storage room. And for this, we make the profiling for each point with the profiling of the velocity and of the direction. So for this case, we build a wireless anemometer. It has a big body and a top plate, and between those there's a small gap. And through this gap, the flow can go through. And in the gap, there's a sensor board. On this sensor board, there are 2 one-dimensional flow sensors. And with this one-dimensional flow sensor, we measure. The sensor is the same as described. We have a heater in the middle, we have 2 thermopiles beneath it, and all of them are placed on a thin membrane because of thermal decoupling. And the principle is also already known. We have the heater, it distributes the temperature. If there's no flow, both thermopiles will measure the same temperature, and if they measure the same temperature, there is no differential of the voltage. If there is a flow, it will shift the heat to one side, and one thermopile will be hotter than the other one, and so we will have the thermal voltage we can measure, a differential voltage we can measure. But how to measure a direction with a one-dimensional sensor? One-dimensional means with a flow sensor which only can measure the velocity. So it's quite easy. We use 2 of them, and we position them orthogonally, as shown here. And if we use this position, we have 2 speed vectors, which are Vx and Vy. And with a little help of Pythagoras, we are able to distinguish the resulting vector and its angular. And so we have our direction and the flow speed. But this version with 2 single chips, there are 2 disadvantages of this version. And one is it's very expensive to use 2, and 2 chips have a higher space requirement on the PCB board. Also, it's not really possible to measure in the center of the board because we can't place both sensors in the center, so we have to place them beneath. And if the flow comes from this direction, goes over this sensor, the distance between the edge and the sensor is not the same as when the flow came from this direction. So we have a little error, a symmetrical error. Another problem is the alignment between those both sensors. It's very tricky to align them directly orthogonal to each other because we do it by hand. Even if you do it by machine, it's not really very good to do it in this way. So also we will have a little alignment error. And it is possible to get rid of those errors by characterization and calibration, but it's very tricky. And so we decided to make a single chip version, and those two-dimensional flow single chip version is shown here. It has a square chip size by 2 millimeters. There are 4 heater wires, as seen here, and beneath 4 thermopiles. And each of the thermopiles depends on 15 thermocouples. And as it's a one-dimensional sensor, we have a membrane, which is not really suitable here, in the middle for the thermal decoupling. So let's come to the fabrication process. We start with a double-side polished silicon wafer as a bulk material. And we need an etch top for a later process step. And so there's a thermal silicon oxide step to oxide the surface of the wafer. And on this etch top layer, we deposit a LPCVD low-stress silicon nitride. This is the oxide layer. And on the top, we have the silicon nitride. And this silicon nitride will become the bottom side of the later membrane. So now we can start with the electronic parts. We have the first thermopile material, which is polysilicon, doped polysilicon, and it's structured in a dry etch process. And on the contact plate between the first and the second thermopile material, we will sputter a thin titanium nitride film. This is a diffusion barrier because the second thermopile material will be tungsten titanium. And the tungsten titanium would diffuse into the polysilicon without the diffusion barrier. And then we will receive short circuits and the chip is destroyed. And the heater structure is made out of the tungsten titanium too. So after finishing the electrical components, we have to cover them to protect them. And we will do this with the same LPCVD low-stress silicon nitride. So we have now a closed membrane. And to get the membrane, to freeze the membrane, there's a dairy process at the end of the process. And for this, we need the etch top because the dairy process will end at the silicon oxide. And there's an additional short wet dip to get rid of the silicon oxide on the backside of the membrane. After the process, we have to characterize the sensor. For the characterization, we build up a special setup. And for this setup, we need a PCB. The PCB looks the same like the one before with a double chip solution. We put the sensor in the middle of it, put the PCB into the setup, and the setup has a rotatable channel. And the channel is connected to a master controller. The master controller gives us 2 SLM constants the whole time. It's with this channel around about 1.6 meters per second. And the channel is rotatable by 360 degrees. And it has an increment of 1 degree. And for the measurement, we need an angle set because we do not want to measure all the 360 degrees. That would take too much time. And we know from further measurements that there are some critical angles. And the critical angles are the 0 and the 90 degree, and the angle of 45 degree in the middle. And to analyze them, we make a subset of angles of plus minus 1, 2, 5, and 10 degrees, and so we can analyze this critical angle. And there's 2 other angles we want to analyze. It's 135 and 180 degrees. And we have a smaller set of sub-angles of plus minus 1 and 5 degrees to analyze them. And we measure 1 minute per angle. And this is around about 300 measuring points per each angle. And the 2 signals we receive is the signal for the TPX pair, those both thermopile pairs, and the TPY pair. And we bring both of them together to look if the sensor does what it should. And here you can see the sets of angle. We have 0, 45, 90, 135, and 180 degrees. And there are the dots. The lines are sinusoids fitted to the data. And what you can see here is one of the worst case of our measurement. We measured 10 or 15, around about 15 sensors, and this was one of our worst one. It's to show that we are able to distinguish an angular resolution of 1 degree. And of course, you cannot see it here directly, so we did a little bit mask statistic, and with this mask statistic, we find out that the worst problem is between the angular between 180 and 181 degree in this case. And if we take a closer look in form of a box plot, we can see that even between those two angles, we are able to distinguish an angular resolution of 1 degree. Because the boxes overlap, but the medians are clearly distinguishable. So let's come to the end. At the beginning, we want to profile the airflow condition in cold storage warehouses. For this case, we need a single chip solution for a two-dimensional flow measurement. Two-dimensional flow measurement means in this case the velocity and the direction at the same time. We build a thermal flow sensor which has 4 heater wires and 4 thermopiles. And it's silicon-based with a silicon nitride membrane for thermal decoupling. And it had a total chip size of 2 by 2 millimeters and an angular resolution of 1 degree. So thanks for your attention. I appreciate your questions.